Today we pick up with the formal definition of the derivative. The formal definition is f prime of x equal to limit as h goes 0, f of x plus h minus f of x all over h. What do you notice is different than what we just did on the board? There's no a. So what this means is instead of at a single point, you can look at it as an entire function. So as you consider this graph right here, oh, by the way, other operators that imply derivative, we can see f prime, that means derivative. Dy over dx, that means derivative. D over dx means derivative. Dx means derivative. These are all things that when you see them, they say take the derivative. And when I say take the derivative, that means this. Kind of like when I say f inverse for the function f of x is, or I'm sorry, y is equal to 2x minus 1. We said, what does that mean you do to x and y? You switch them. That's what this -1 means, okay? So when you see f prime or dy over dx or d over dx, it means to do that. That's what it means. So what we're going to do is we're going to look at this graph, which is f of x right here, and we're going to try to make a table of values for f prime of x, and we're going to sketch the graph of f prime. So, for example, I'm going to look at this spot right here, and this spot right here, and this spot right there. I think that those are really interesting points, because if I have an x value of -3, what is the derivative at -3? If you were to draw the slope of the line tangent, what would it be? 0. So f prime of x is going to have a value of 0 at -3. If I were to look at 0 here, what is the slope of the graph at 0? 0. I'm writing a little bit too large. Going to make some space here. And if I check at 2, the slope again is 0. So what that means is the graph of f prime of x is going to cross the x-axis at those positions. The graph of f prime of x is going to cross the x-axis at -3, at 0, and at 2. So I want you to look on this side now. We're going to choose values that are less than -3. Can you tell me something about the derivative of the graph for x values that are less than -3? They're negative, right? And if we're going to draw the graph of the derivative, if the graph of the derivative is negative, what does it mean for a graph to be negative? Where does it sit if it's negative? It sits below the x-axis. So you can see for all values that are less than -3, we'll say like -4, that f prime of x is going to have negative values. So therefore, it's going to sit below the x-axis. Everybody see? Negative slope, so therefore the graph sits below the x-axis. What can you tell me about the slope between -2 or -3 and 0? So we get -1. It's all positive, right? Well, if the graph is positive, it should sit above the x-axis. If I choose a value, say 1, what is the slope between 0 and 2? It's negative, right? In fact, I want you to understand at this spot, wouldn't you agree that at 1, the slope is approximately, say, -2? So you could even put a value there and say, hey, at 1, the graph has a slope of about -2. And then once we get to 2, what happens after that? derivative is positive. So therefore, it should sit above the x-axis the rest of the way. This is the graph of the derivative of this function. I want you to visit with a peer for 45 seconds and talk about the similarities and differences between these functions. Come up with anything. Go. Okay, let's come back together. What can you tell me about the two functions? How are they what either similarity or difference? What do you got? Oh, interesting. As you can see, Riker's pointed out here that you have 1, 2, 3, 4 times it crosses the x-axis. This one crosses the x-axis 3 times. In fact, wouldn't you say that this is an x to the 4th? And this is an x cubed? It just so happens when you take the derivative of a function, the power ends up being reduced by 1 every single time. Any other thoughts? Yeah. Okay, very good. Okay, flip it upside down, you got an M. Flip it upside down, looks like an N. Part of the relationship is that these are both polynomials, right? When you take the derivative of a polynomial, you're going to get another polynomial. Okay, that will happen. Okay, but I do want you to notice that here you have kind of you have these 3 kind of bumps here, whereas here you only have 2. You can see that the degree of the polynomial is reduced by 1. And so we're going to talk about what it means to be differentiable. In order for a function to be differentiable at point A, f prime of A must exist. And so right now you're trying to think of, well, if a function's not differentiable at point A, what would that look like? And here's an example of where a function is not differentiable. Anybody want to guess what x value that function is not differentiable at? At x equals -1. Because it's discontinuous. You must know where functions are differentiable and where they're not. Differentiable means you can take the derivative. That's one classic example. Here's another classic example where a function is not differentiable. You may want to guess what x value can't take the derivative there? At 1. This has what we call a corner. And part of what we're not going to get too deep into, but we're going to realize that in order to be differentiable, the derivative from the left must be the same as the derivative from the right. Does that sound familiar? Yeah, in order for a limit to exist, the limit must be the same from the left as it is from the right. Same thing with differentiability. You can see the derivative from the left is positive. Yes, and the derivative from the right is negative. They are not going to just all of a sudden even out at 0. And so therefore, at a corner, you cannot take a derivative. And then here's one more. This is kind of tricky. We're going to see if you guys can guess the x value for where you do not have differentiability there. Why at 2? Because the slope is undefined. We have what we call a vertical tangent. So if you ever have a vertical tangent on a graph, you may not take the derivative at that spot. Those are the 3 normal examples of where you do not have differentiability. Flip it over. Whoa, what happened there? Okay, it says identify intervals on which the function has a derivative that is positive and negative. Also identify points at which the function has a derivative that is 0 and points at which the function is not differentiable. So let's look at this example right here. Can somebody tell me an interval where the derivative is positive? -2 to -1, good. It's positive there. Where else is it positive? One to 2. Can somebody tell me where the derivative is negative? Good. -1 to 0. Where else? 2 to 3. Where else? Yeah, we'll say -3 to -2. Where else? 0 to 1. Notice how you guys broke it up so that you did not state that 0 was included in that interval because you can't take the derivative there. So now let's talk about where the derivative is 0. Anybody see a spot on here where the derivative is 0? That's the only spot, x equals 1. Anybody want to guess where the derivative is not differentiable, where we cannot take the derivative? -2. 0. 2. -1. Everybody clear? I'm looking for where derivatives are 0, where they're positive, and where it's not differentiable. Great. Then what we're going to move on to is this is what your assignment's going to look like. You're going to be given a graph, and you want to be able to identify what the derivative looks like. Is there any spot here where you can't take the derivative? Any spot where you can't take the derivative? Nope. Is there any spot here where the derivative is 0? Where? Yeah, so I'm going to put a 0 at -3. Another spot where the derivative is 0. Another spot? 3. Okay, so we said there's no points where it's not differentiable. Those are spots where derivative is 0. So is the derivative positive or negative during this region? So therefore the graph should be above the x-axis. How about here? Should be below the x-axis. How about here? Positive, and here? Negative. So I want to be above, below, above, below, above. So that'll be approximately the derivative graph of the function that was shown. Is there any spot here where you cannot take the derivative? Why? That's a corner. So you cannot take the derivative here. So I'm just going to put an X to remind myself I cannot have a function value for the derivative at that spot. Okay, I'm going to show you what that looks like. Is the derivative ever equal to 0? No. In fact, if you were to estimate the value of the derivative here, what would it be? Do you agree that derivative is constant here? You always have the same slope? Is it positive or negative? Negative. I would approximate it to be -1. Are you guys okay with that? What would you approximate the derivative to be over here? +1. So that means that this graph here, the derivative, is going to have a constant value of -1 the entire time. I can't take the derivative at 0. So therefore, the derivative function must have an open value there. And then it jumps up to 1. That would be a pretty accurate description of the graph of the derivative. What can you tell me about the next graph? The derivative is constant. The slope is constant. Estimate the slope. 2, okay. You're saying the slope is 2, so that means I'm going to have a constant value of 2. The next one's kind of challenging. Could be better off if you just come up with a thought on your own. Talk with a partner, spend about a minute, try to come up with a graph of the derivative of that. Go. Okay, let's think about it. This is a tough one. This could tell Lava where you're at. I was able to see kind of some things people are doing. Tell me something. Okay, it's going to cross through 0 right here. Is everybody clear there? The derivative is equal to 0, 0. Great. Then tell me something about the derivative here. It's positive. So therefore, it will sit above the x-axis, correct? And then what about here? It's negative, so it needs to be below the x-axis. So those are the first really two things that you got to have to get partial credit for this piece. Must sit above the x-axis, must sit below, must cross through 0. Now let's get a little bit more technical, okay? Look at the derivative right here. If you were to estimate the slope, what would you estimate the slope to be right here? What did you say? It's about 0? But it's positive, right? You would say 0 on the positive side. What would you estimate to be the slope here? 0, but it's definitely negative, right? So we want to be close to 0 on the positive. We want to be close to 0 on the negative. Can somebody tell me where my slope is the steepest? Like you're like, that's the greatest value. That's the highest value of that function for its slope. I'm going to say right about here, right? So I'm going to say that that has a slope of about, say, 2 or 3. So I'm going to say that it has a value of about 2 or 3 right at that spot. When is this one most negative as its most negative value? Right about here? Wouldn't you say it's a slope of about -2 or -3 right there? So the actual derivative looks like this. Now, I have to admit that a few of you guys were just about spot on, which is excellent to see that this is really starting to kick in for you. We did practice this actually over multiple days, but you're getting, hopefully, the idea. And after seeing enough examples, hopefully it will really click for you. Flip over to the next page. We have 2 more we want to look at together. Look at this one all on your own, okay? Give you 30 seconds. Go. All right, anybody a thought? Straight line at 0. Everybody agree that the derivative is always 0? So therefore, its derivative will sit right on the x-axis. Let's tackle this one together. What's the first thing you notice? Tell me something you notice about this guy. It's whacked. Awesome. What else? 0 at -2. And at 1/2. And at -1/2. I heard somebody say 4. Who said 4? Okay, you are very, very close, and I thank you for bringing that up. We would say close to 0, but definitely negative. Would everybody agree that it's going to be close to 0, but that the slope is definitely negative right there? Is there a spot where you can't take the derivative here? Yeah, about 1.5. Looks like there's a vertical asymptote there. Let's think about the derivative near that vertical asymptote. Let's look on the right side of the vertical asymptote. What would you say about the slope right here? Everybody agrees super negative. So if the derivative is super negative, where should the graph be located? Way down, right? Like way down here. See, this red graph is the derivative. It tells us the slope. It tells us the slope is always negative because it's sitting below the x-axis. You tell at the beginning it's really negative, and up here it's a lot less negative. Let's look at the derivative on this side. Let's look at the left-hand side. What can you say about the slope here? So the graph should be sitting way above the x-axis, right? All right, let's look at our intervals in between. Positive or negative for slope here? Positive, so it has to sit above the x-axis. How about here? Positive, it needs to sit above the x-axis. How about here? Negative, and here? positive. So I'm going to say that the graph is going to look something like this. Above the x-axis, still above, and then it dips below. That's a really good view of a possible derivative. Okay, I'm going to hand out your sign.